SwayamPrabha.
Welcome. So in the last class we have looked at how we can have a two-factor approximation algorithm using the F-factor approximation algorithm for set cover. In this class we will have a direct approach for having a two-factor approximation algorithm for vertex cover. So two-factor approximation algorithm for vertex cover. We can solve the general weighted version. So each vertex, what is the input? A graph G equal to V comma E, and there is a weight function from V to real numbers, non-negative weights. Okay, and what is the output? A vertex covered of minimum total weight. So let's write the LP for vertex cover. First write ILP, minimize for each vertex. I have a variable, so C of V xv, this variable takes value 1 if we pick the vertex cover, otherwise it takes value 0. This is V in V subject to the constraints. We have a constraint for each edge. So for each edge E equal to U comma V in E, what are the constraints we have? XU plus XV, this is greater than equal to 1, and for each vertex V in V XV, this is greater than this is in between in the set 0 and 1. So this is the ILP. So what is the LP relaxation? Minimize summation V in V CV XB subject to for each edge E equal to U comma V in E XU plus XV is greater than equal to 1, and X for every vertex V in V XV is in between, is greater than equal to 0 and less than equal to 1. But again, because we are minimizing it and the objective function is monotonically increasing with XV, we can drop the condition that XV less than equal to 1. without changing the optimal value. Okay. Now we claim that this optimal solution and an okay, so it follows from, so here is a fact, there in every feasible and bounded, that means where the maximum or minimum is not infinity or minus infinity, in every feasible and bounded linear program, um, there exist there exists uh, there exists an optimal solution which is an extreme point. Moreover, such a solution can be computed in polynomial time. Okay. A solution to an LP is called half integral if each of the variable each of if each variable each of its variables take value in 0, half, 1. Okay. So the claim is that for vertex covered, the LP has a extreme point. Actually, all extreme point solutions of the vertex cover, all extreme points are half integral. In particular, the extreme point or those extreme points which are optimal solutions, they are also half integral. So here is the lemma. This is called Nemhauser-Trotter theorem. Due to this, let X be a solution to the vertex covered LP. Suppose X is not half integral. then X is not an extreme point solution of LP. That means all extreme point solutions of the LP must be half integral. That is, all extreme point solutions must be half integral. Proof. So, proof by contradiction. So, let X equal to XV, V in V, be a solution which is not half integral. Okay, so then define the following sets. V greater than half is those vertices such that X of V belongs to half and 1 is more than half, and V less than half V such that X of V belongs to 0 comma half. Of course, V half is set of vertices V such that X of V is equal to half. Okay, now using these sets we define another solution, another two solution, and show that this is a convex combination of those two solutions. X is a convex combination of those two solutions. So, for epsilon greater than 0, define the following two solutions. Okay. So, what is YV? One is Y, another is Z. YV is XV plus epsilon if V belongs to V greater than half, XV minus epsilon if V belongs to V less than half, and this is XV if V belongs to V half. This is YV. ZV, you define ZV as XV minus half if V belongs to V less than half, XV plus epsilon, XV minus epsilon if V belongs to V less than half, if V belongs to V greater than half, and this is XV if V belongs to V half. Okay. Now, since V greater than half and there are some vertices where which X assigns more than half value, and there is between half and 1. So, let us make this also, because there are some values which on this part make it otherwise. So, YV adds the value of epsilon for those variables which are which belongs to V greater than half, and reduces its value by epsilon for those variables whose value is in between 0 and half. Okay, and ZV does exactly opposite. Now, because X is not half integral, there exists at least one vertex in V half, V greater than half, or V less than half. That is since V greater than half union V less than half is not equal to empty set, X, since this we have X, Y and Z are all distinct. Also, we can see that X equal to half Y plus Z, that is X is a convex combination of Y and Z. Okay. So, define Y equal to YV, V in V, and Z equal to ZV, V in V. So, next we claim, to finish the proof, Y and Z are solutions of the LP. Okay. So, proof. First, observe that we can choose epsilon small enough so that after this addition and subtraction of epsilon, these vertices remain in corresponding sets. So, choose epsilon less than, what is the thing, minimum of these sets, xv minus half mod that xv v belongs to v greater than half union v less than half. So with this choice of epsilon, so let me put a half also. So with this choice of epsilon, mm, we observe that x v belongs to v less than half if and only if yv belongs to v less than half. Same, xv belongs to v greater than half if and only if yv belongs to v greater than half. Same with zv, xv belongs to v greater than half if and only if yv belongs to v greater than half. xv belongs to v less than half if and only if yv belongs to v less than half. So first of all, then these new claimed solutions y and z satisfy these constraints. They are all positive, and also next we need to show that these each constraints are also satisfied with y and z. So let E equal to u comma v E be an arbitrary edge. Okay, so we have x satisfy this constraint. So xv plus xu plus xv, this is greater than equal to 1. So what are the possible values of what are the possible cases? So case 1, xu is greater than half. If xu is greater than half, then sub case xv is also greater than half. Then we have, in this case, if xu is greater than half, then we have yu is also greater than half and zu is also greater than half. In this case, if xv is greater than half, we have yv is also greater than half and zv is also greater than half. Hence, this implies yu plus yv is greater than 1 and zu plus zv is greater than 1. For this case, if xv is greater than half, then it is satisfied. Let's do the next sub case. Xv is less than half. So, first of all, make slight change. If x u belongs to v of v greater than half. If xu is 1, then yu is 1 and zdu is also 1, nothing to prove. So, this do this, and also this is also xv belongs to v greater than half. So, in this case, xv belongs to v less than half. In this case, we have yv also, v belongs to in this case we have xu plus xv equal to yu plus yv equal to zu plus zv. Okay, and because xu plus xv is 1, in this case also the conditions are met. This is v. So, similarly, the other subcase can be done. Other case 2, u belongs to v less than half. Subcase 1, v belongs to v greater than half. In this case also we have 1 equal to xu plus xv, which is equal to yu plus yv, which is equal to zu plus zv. Okay, and hence the age constraint is satisfied. Subcase 2, v belongs to v less than half, but if both u and v cannot belong to v less than half, if both values are less than half, xu and xv is less than half, this implies xu plus xv is less than 1, which contradicts that x is a solution. Okay, so this case cannot happen. In the other 3 cases, we have shown that this y and z also satisfies the constraint. So, hence y and z are also solutions of LP. But before we have already seen that this is a convex combination. So, hence x is not an extreme point. Hence, x is not an extreme point, which finishes the proof. Okay, so let's stop here. Using this, exploiting this structure, we will design a two-factor approximation algorithm in the next class. Okay.